Hi class. Before we get started in section 9.3, which is about the convergence of a series, I want to review some of the things that we've talked about so far in chapter 9. First thing we did in chapter 9 is we talked about a sequence, and we said a sequence was just a list of numbers that probably are going to follow some kind of a pattern. Okay, for example, we might end up with a sequence that goes 1/2 and then 2/3 and 3/4 and so on. And we talked about how we could describe the nth term of this sequence. And for this particular sequence, I guess we could say that the nth term is going to be just n divided by n plus 1. All right, so if we wanted to know, like, what's the 10th term in this sequence, we could say, well, just plug in 10 for n, and we'd have 10 over 11. Okay, so we talked about that, and we talked about the limit of a sequence. And what we were interested in looking at was what's the limit as n goes to infinity of the nth term. And in this particular case, the nth term is going to go to, this will be the limit as n goes to infinity of n divided by n plus 1. And we can kind of tell on this one, I think, if you just think about putting in a very large number, n and n plus 1 are going to be relatively the same size. For example, 1,000,000 divided by 1,000,001 is going to be pretty close to 1. Right? You're going to see that a lot of these problems you can also apply L'Hopital's rule. As n goes to infinity, this goes to an intermediate form of infinity over infinity. Take the derivative of the numerator and denominator, and you're going to get 1 either way. All right, so then we switched gears in section 9.2, and we talked about what it means for to talk about a series. All right, and a series, we said, looks a lot like a sequence, except a series is the sum of all the terms in a sequence. Right, so it's going to be a sub 1 plus a sub 2 plus, and so on. Right, and essentially we're going to end up adding up an infinite number of these, are the more interesting types. All right, so in order for us to talk about whether or not a series is going to converge or diverge, what we want to look at is sometimes we're going to end up adding up an infinite number of terms that adds up to a finite number. And if that is the case, we say that the series converges. If that's not the case, we say that the series diverges. Right, and I think in class we talked about what our intuition tells us about adding up an infinite number of positive numbers. I think most of our intuition says that's going to go to infinity, but we saw in class if we take a series that looks like 8 plus 4 plus 2 plus 1 plus ... and if we add up an infinite number of these things, this thing is actually going to converge to a particular number. And I think we demonstrated that in class by having the student walk towards the door. So there is a series, this is an example of a series that converges. And then we said that any kind of a series that is in this kind of a pattern is going to converge. And we said that if a series was geometric, and a geometric series just means take the first term and then multiply that term by, your book uses x, multiply that again by x, and multiply again by x, and keep doing this on and on forever. The nth term is going to be a times x to the n minus 1, and continue on and on and on. We said that this was going to converge, and it would converge to a divided by 1 minus x. All right, but this only converges whenever x is between -1 and 1. All right, that was our first kind of a test for a series to determine if something is going to converge or diverge. And our first test is, check to see if it's geometric. If the common ratio is between -1 and 1, it converges. And not only does it converge, we know what it converges to. We're going to be getting into some different kinds of series that are not necessarily geometric. And we still want to be able to answer the question, does the series converge or does it diverge? So in this section 9.3, we're going to talk about, there's a couple of theorems in here, and a couple of things that are just called tests for determining if something is going to converge or diverge. All right, so the first thing I want to look at is what does it mean for the series to converge? We're going to be looking at a sequence of partial sums, and we're just going to say the first partial sum is just equal to whatever the first term happens to be in the series. Okay, the second partial sum is the first term plus the second term. The third partial sum is the first term plus the second term plus the third term, and so on. And if we could come up with some kind of an expression for S sub n, is going to be the sum of all of these terms. And if we can come up with some kind of a formula for this, then we can determine if it's going to converge and what it converges to. All right, so first thing is we've got a couple of theorems about series and converging. So first one is this. Suppose the sum, and I'm going to start writing this in sigma notation, the sum from n equals 1 to infinity of a sub n and the sum n goes from 1 to infinity of b sub n. Suppose that these both converge. And let's say that k is just a constant. All right, from here, there's a couple of theorems that are a couple of things that are going to follow. First thing is, if we were to take these two series and add them together and say the sum from n to infinity and take all these a sub n's and add them to all of the b sub n's, okay, that this new series also converges. And not only that, but it's equal to the sum of the whatever these converge to. So it would be the sum from n to goes from 1 to infinity of a sub n plus the sum n goes from 1 to infinity of b sub n. Right, that seems kind of intuitive, I think. Okay, then the other one is if we take all the terms in a series and we multiply them by a constant and we add them all up. All right. You can think of this as an infinite number of terms. They all have a common factor. We can take that common factor out and we'd end up with the sum from 1 to infinity of a sub n. All right, so if the sum of all these a sub n's converges, then if we multiply everything by a constant, the new series is also going to converge. All right, and again, it seems to me like that's kind of intuitive. All right, the third thing is if we, let's call this number 1, number 2, if a finite number of terms are added or deleted from the sum n goes from 1 to infinity of a sub n, then the convergence of the sum does not change. Okay, for example, we saw the series 8 plus 4 plus 2 plus 1 plus, we saw that this converges. Okay, now if I were to add, let's say, another term here, 16, this series is still going to converge. It's going to converge to another number that's going to actually be 16 more than what this other one converged to, but it's still going to converge. Also, if we were to eliminate some of these terms, whatever is left over is still going to converge. Okay, as long as we either add or delete a finite number of terms. Okay, we can't add or delete an infinite number of terms, otherwise it doesn't apply. Okay, the third thing here is actually what I would call the nth term test. Okay, and the nth term test says this. This is a test to see if a series is going to diverge only. And it says that if the limit as n goes to infinity of a sub n is something other than 0, then the series diverges. Okay, if the nth term doesn't go to 0, the series is going to diverge. For example, if we took the sum n goes from 1 to infinity and we took n divided by n plus 1, all right, if we think about what these terms are going to look like, this is going to be a half plus 2/3 plus 3/4 and so on. The nth term here is going to be n over n plus 1, and then we're going to continue to add terms continue to add an infinite number of terms like this. This number is getting pretty close to 1, so eventually this series is going to act like adding 1 plus 1 plus 1 plus 1 plus 1, which is going to end up just going to infinity. All right, now we have to be kind of careful, we have to be very careful with this theorem. The nth term test is a test for divergence. Okay, it's not an if and only if. It says that if the nth term doesn't go to 0, then the series diverges. It doesn't say that if the nth term goes to 0, the series converges. Okay, that's a very important thing. And most of the series we're going to be working with have the nth term go to 0. Sometimes these series will converge, sometimes these series will diverge. Okay, so make sure that you understand this, that if the nth term doesn't go to 0, series diverges. It's not an if and only if. It's not if this doesn't go to, or if this does go to 0, then the series converges. That's not true. Okay, so the last thing is fourth one. If the sum of a sub n diverges, then the sum of a constant times a sub n also diverges. Okay, and again, I think that that's fairly intuitive. Here we got to say that k's got to be something other than 0. All right, if k is equal to 0, then this is very trivial, that it's going to converge to 0 because they're all going to add up to 0. Okay, so now what we're going to end up doing through this chapter is building up some kind of a toolbox for determining whether or not series are going to converge or diverge. So far, the tools that we have are geometric series, common ratios between -1 and 1, converges. We also just saw the nth term test. If the nth term does not go to 0, then the series diverges. All right, and then last Wednesday, I gave you guys a question, and I said, what happens to this series? Okay, and I took a poll, and it seemed like about 2/3 of you said converge, and about 1/3 of you said diverge. All right, so what I want to look at is how we can determine whether or not this is going to converge or whether it's going to diverge. It's certainly not geometric. Okay, so we can't use the geometric test. Also, the nth term does go to 0, right? But again, because the nth term goes to 0, that's not conclusive. So we got to look at another way of checking this answer. All right, and I want to go through this with a couple different ways. And the first way that I want to do this, I think, is fairly intuitive. All right, so let's say that this is my sum. 1 plus 1/2 plus 1/3, 1/4, 1/5, 1/6. Let's say we go up to 1/8, and then 1/9, and we go up to 1/16. And I think you'll see why I'm doing this in a minute. All right, so this is the sum. This is the sum of all these terms up here. Okay, then what I want to do is compare this to something else. And I want to compare this to 1 plus 1/2. And then I'm going to change a couple terms in here. I'm going to make this plus 1/4 plus 1/4 plus 1/8, 1/8 up to 1/8, and then plus 1/16 up to this 1/16, and then do the same thing here for 1/32 and do all those. All right, so all I'm doing is I'm changing some of the terms. The terms that are in red have replaced the terms up above. So I replaced this 1/3 with a 1/4. I replaced this 1/5, 1/6, 1/7, all with 1/8. I replaced the 1/9 up to 1/16 with 1/16. Okay, and then I want to know what's going to happen to this new series. All right, so if we look at combining some terms here, all right, there's 1, there's a 1/2. These two things are going to add up to 1/2. I've got 1/8 in here. It replaced 1/5, 1/6, 1/7, and 1/8. There's 4 1/8s in there that are going to add up to a 1/2. And then I replaced a bunch of these terms over here with 1/16, and there's actually 8 of them that got replaced with 1/16, so that's going to add up to a half. So what we're going to end up with is 1 plus a half, plus a half, plus a half, plus a half, and so on. All right, so we're going to end up adding up an infinite number of halves, and by the nature of that, this is going to diverge. Okay, an infinite number of halves is going to end up giving me an infinitely large number. All right, so that's a trick on this one, and by the way, this thing is called the harmonic series. And the harmonic series is one that we're going to end up taking a look at a couple different times. All right, but what I want to use is, I want to say something about this harmonic series also about another way that we could check to see if it's going to converge or diverge. All right, in chapter 8, we looked at an integral, and we looked at the integral from 1 to infinity. And one of those that we looked at was 1 over x dx. All right, and we said this was the limit as b goes to infinity, and then we wrote it as an integral from 1 to b, and then 1 over x dx. All right, we took an antiderivative of 1 over x and got natural log. So this will be the limit as b goes to infinity of natural log of x at 1 and b, and we ended up with the limit as b goes to infinity of natural log of b minus the natural log of 1, and we said that this ended up just being equal to 0, but the natural log of an infinitely large number went to infinity. We said that this integral diverged. All right, and so essentially what we were saying was that if you look at the graph of this, 1 over x looks something like this, and we said that if we integrate from 1 to infinity, that essentially this area would be infinitely large. All right, so what I want to look at is, what does that have to do with this harmonic series? All right, so what I want to do with the harmonic series is I want to fill in some things that will represent the numbers of this series that we're going to add up. So this is the graph of y equals 1 over x. All right, so if I draw a rectangle here that goes from 1 to 2, the height of this rectangle is going to be what I get when I plug 1 in here. And then if I plug in 2, we're going to end up with, this function takes on the value of a half. So we're going to end up with a rectangle that looks like that. And then when x is equal to 3, we'll get a rectangle that looks like this, and so on. All right, so if you think about what do each of these terms represent in the series, the area of this rectangle is 1, the area of this rectangle is a half, the area of this one is a third, and I can continue to do that on and on and on. All right, so what we want to think about is, how does the area of all those rectangles compare to the area underneath the curve? All right, the area of all those green rectangles is greater than the area underneath the curve. All right, so we can say the sum of 1 over n, which is equal to 1 plus 1/2 plus a third plus ... This is bigger than the area underneath the curve, which we said was this, which was the integral from 1 to infinity of 1 over x dx. All right, and then we said that this was infinitely large. All right, so here's the argument then. This number is infinitely large. This series is bigger than something that's infinitely large. All right, so if this series is bigger than something that's infinitely large, it has to go to infinity as well. All right, so this series is going to diverge. Okay, and the reason it does is because there's this little area out here outside each one of these that ends up being more than the area underneath the curve. Okay, so again, the harmonic series, this is one that we're going to have to remember. The harmonic series diverges. All right, it's not something that I think is very intuitive, but I've given you two arguments about why this series would diverge. Okay, so I guess I want to take a look at another one then, and that is, what if our series is 1 plus 1 1/2 plus 1 over 4, sorry, make that 1 plus 1/4 plus 1/9 plus 1/16, and so on. So the nth term is 1 over n squared. Converge or diverge? All right, so I guess we could look at this and say, is it geometric? And the answer is no. If you look at these first two terms, the common ratio would have to be a fourth, but if the common ratio was 1/4, this next term would be 1/16 instead of 1/9. All right, so it's not geometric. Next thing we can look at is, does the nth term go to 0? All right, well, the nth term is 1 over n squared. 1 over n squared does go to 0 as n goes to infinity. That's not conclusive. All right, so what we want to look at next is, can I compare this to an integral? All right, and I think the integral that I want to compare this to is 1 over x squared. All right, so let's look at the graph of 1 over x squared. All right, and then if we play that same game again and say, all right, let's go here to 1, and let's fill in a rectangle. Let's put these in green again. We put in 1 over, or 1, and we put in 2, and we put in 3, and so on. All right, so as I plug in 1, 2, and 3, we're going to end up getting that the area of this thing is 1, the area of this thing is a fourth, the area of this is a ninth, and so on. Okay? Then, what we want to be able to do is, I'd like to be able to compare this series, 1 plus 1/4 plus 1/9 plus 1/16, and so on. I'd like to compare that to the integral from 1 to infinity of 1 over x squared dx. Okay, and then looking at the picture, I think we can argue that the sum of the series is bigger than the integral. Right? Now the problem is, this thing, 1 over x squared, is a p integral, and p is equal to 2, and if you remember from chapter 8, this is something that we wanted to look at again, and I told you it's going to come back. Because p is bigger than 1, this thing converges. Okay, and that kind of blows up our argument, because if it converges, that means that this is a finite number. We're saying that these numbers are going to add up to something that's bigger than a finite number. Right? And the argument is, if something is bigger than a finite number, does not necessarily mean that it's infinitely large. Okay, it just means that it's going to be bigger than whatever this number happens to be. All right, so we have to make a little bit of an adjustment here. And the adjustment that I want to look at is, I'm going to take every one of these rectangles in this picture, and I'm just going to slide them over 1 unit. So take this rectangle, slide it over 1 unit. Take this one and slide it over. This one, slide it over, and so on. So now we end up with all of these red rectangles. Okay? And I want to compare the sum of all those red rectangles to this integral again. All right, so the problem is that we have this one here. And I'm going to say, let's just eliminate this one and eliminate this one. Right, when we eliminate that, it doesn't change whether or not this series converges or not. It just changes the number that it converges to. Getting rid of this term is going to create a picture that looks like this with all these rectangles. And now I think we can argue that the sum of all of these is going to be less than the integral. All right, and if the sum of all these converges, then adding 1 to it is still going to converge. All right, so the argument is that we don't have to always do an upper approximation or a lower approximation. Our conclusion here is going to be something called the integral test. And the integral test says this. It says, suppose a sub n greater than 0 is equal to some function, we'll say f of n, where f of x is decreasing and f of x is positive. Okay, and then our conclusion here is if the integral, and there's the 1 down here on the bottom is kind of arbitrary, from something to infinity of f of x dx converges, then the series n goes from 1 to infinity of a sub n also converges. Second part is, if the integral from 1 to infinity of f of x dx diverges, then the series n goes from 1 to infinity of a sub n also diverges. Okay, so basically we're saying that whatever, if we can come up with some kind of a function that resembles the nth term, and that function is always positive and decreasing, then whatever the integral does, the series does exactly the same thing. All right, so for example, suppose we wanted to know something about the series that starts with 1 and then plus 1 over the square root of 2 plus 1 over the square root of 3 plus, and so on. So the nth term is 1 over the square root of n. And we want to know, does this series converge or does it diverge? All right, so we don't really have to go through and evaluate the integral. All we really need to do is say, suppose that f of x is equal to 1 over the square root of x. Okay, it looks like this expression, only it's a function of x. All right, so then all we have to do is look at, what is the integral from 1 to infinity of 1 over the square root of x dx do? All right, so you've got to remember that this is a p integral. In this case, p is equal to 1/2. That number is less than 1, therefore this integral diverges. And if the integral diverges, then the series of 1 over the square root of n also diverges. And so the integral test is kind of a nice way to compare something to an integral, and if the integral converges, then the series converges, and if the integral diverges, then the series diverges. All right, so let's take a look at another example. All right, suppose we're interested in a series that the nth term is 1 over 1 plus n squared. Okay, and we want to know, is this going to converge or is it going to diverge? All right, so the series looks like this. It's going to be, when n is equal to 1, we're going to end up with 1 over 2. When n is equal to 2, we're going to get 1 over 5. When n is equal to 3, we're going to get 1 over 10, and so on. So we want to know what happens to this series. Well, if we say the function f of x is equal to 1 over 1 plus x squared, and we want to know is what's going to happen to this integral if I go from 1 to infinity of 1 over 1 plus x squared dx. Remember, our conclusion was that if this converges, then the series converges. If this diverges, the series diverges. All right, I want to show you two ways that we can do this. Okay, one way is we could say, well, we could say this, that we could compare this to 1 over, or I'm sorry, the integral from 1 to infinity of 1 over x squared dx. All right, this is probably the easiest argument. This denominator is smaller than this denominator, which means that this fraction is actually smaller than this fraction. Okay? The next argument is this converges. And it converges because p is equal to 2, and 2 is greater than 1. This converges, therefore this converges. And if this converges, then this converges. All right, so it's kind of a domino effect. This is smaller than this one converges, therefore this has to converge. If this integral converges, then so does the series. Okay, now the other thing we could do here is we could say, well, what does this converge to? We could say the limit as b goes to infinity, the integral from 1 to b, 1 over 1 plus x squared dx. Right, this integral is going to give me arctangent of x. We're going to go from 1 to b, and then we're looking at the limit as b goes to infinity. All right, so we get limit b goes to infinity, arctan of b minus arctan of 1. All right, this number is pi over 4. Right, the reason it is because when we say arctangent of 1, we're saying what angle has a tangent that's equal to 1. Okay, and then this one, we're saying what's an angle whose tangent is infinitely large. All right, if you remember, the tangent function is it's got asymptotes in it, and the asymptotes are at, one of them is at pi over 2. Okay, or you could say what angle has an infinitely large tangent ratio. All right, if you think about a triangle that looks something like this, and you say this is opposite and this is adjacent, and this is the angle, let's say x, the angle that's going to give me an infinitely large opposite over adjacent is when this angle gets to be just about 90 degrees, right, or pi over 2. All right, so this integral converges to pi over 4. Okay, the pi over 4 isn't all that important. The thing is that this converges. And if this converges, then so does this. Okay, so fairly easy argument. One thing converges, the other one's going to converge. Okay, so let's look at just one more of these. Suppose that we have a series, and that series is defined as n goes from 1 to infinity, and our series is n divided by e to the n squared, or just n over e to the n squared. All right, and the question is, does this converge or does it diverge? All right, so this is all about the integral test, so I think we're going to check to see what happens to the integral from 1 to infinity, and our function will be x divided by e to the x squared dx, which may be easier to write if I say 1 to infinity of x e to the negative x squared dx. All right, so we're looking at what's the limit as b goes to infinity, integral from 1 to b of x e to the negative x squared dx. All right, so on this one I think if I do a u substitution, let u be negative x squared, du will be negative 2x dx, and when we substitute in, we're going to end up with an integral of e to the u, and then dx is going to be equal to, or x times dx is equal to negative 2 du. All right, so an antiderivative of this is going to be negative 2 e to the u, which is just negative x squared. And then we're going from 1 to b, and we're looking at what happens as b goes to infinity. All right, so if I plug in b here, we're going to get negative 2 e to the negative b squared is the same thing as this, and then minus negative 2 divided by e to the first power. All right, and then limit as b goes to infinity. All right, as b goes to infinity, this is going to go to 0, and this is going to just end up being 2 divided by e. So this goes to 2 divided by e. All right, and because that's a finite number, this converges. All right, so going back and filling in the details then, this converges. If that converges, then so does this corresponding series. All right, now one of the last things I want to talk about is something that was in Chapter 8 when we were doing the integral test. And we have a whole new family of series that we know is going to converge now. Anything that's in the form of a summation where n goes from 1 to infinity, and our series is something like 1 over n to the p power, this series converges if p is bigger than 1 and diverges if p is less than or equal to 1. Okay, and this comes from what we did in Chapter 8 with the integral, right, with an improper integral. All right, so this gives us a new family of series that we can determine if it's going to converge or diverge, and it's really just based upon the integral test. All right, so for homework, I would like you guys to work on section 9.3. A lot of that 9.3 is about the integral test, and all you're going to do basically on those problems is set up an integral of a function that resembles the nth term of the series and determine if that improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. All right, so work on that for next Thursday, and if you've got any major questions, send me an email. I'll be on my email this week, and we'll tie everything up when I get back from my trip. Okay, thanks, good luck, and keep working on the homework. This is a section you really want to keep up on. So, all right, that's it. Talk to you later. Bye.